A typical problem that you encounter when performing many-body numerics is the problem of dimensionality. Effectively, that when you're writing some code and you're going to go from a one-dimensional system to a two-dimensional system, you have to take into account many different orderings, and a lot of tedious things start to appear that otherwise you would expect to want to easily code. And so today I'd like to present some of the newest features that we've added into Aleph for basically simplifying this and actually solving this headache for you using the lattice class that we've introduced earlier this year, or last year I should say, as of the date of this recording, and basically how to use this new model class that uses the lattice class to spawn structured operator products and sums as a way to then start your numerics, either do exact techniques or tensor techniques. So here we're in the workshop, and so I'm going to run through a couple files to make things more concrete. So the prerequisites for this, I will expect you guys to have agents set up, to have an understanding of how to navigate the workshop, and some background, some familiarity with the lattice class. So if you are not familiar, you could go here directly to the lattice document, and this is basically a primer on it with some examples, and of course there's more. There's tutorials here as well that involve using lattice. And so using this, we're going to use these as an entry point to do some numerics. So when would this occur? Primarily, like I said at the beginning, what we really want to do is we want to study physics or many-body physics at a different dimensionality, so whether in 1D, 2D, or 3D. And when you have to actually address this, it becomes, numerically, it becomes tedious, because as your dimensionality increases, we have different connections and bonds between different sites and quantum degrees of freedom, and then it becomes very tedious to track everything. So numerically, you may want to scale your algorithm from 1D to 2D, and it becomes kind of annoying to work with. So in Aleph, we kind of bundle all this together, or this problem and solution, using a new class called model. Model is effectively a class that, given some rules, will generate a lattice, will take in some lattice information and generate everything you need to get started. And by that, really, it generates an operator product or an operator sum that you can use to then do any kind of operation you would do from many-body physics. Really, what model is made up of is a lattice object and interactions on the lattice. So all you have to do is make a lattice object that you care about. In 2D, there's only a small amount, but there are many different ways you can actually have things interact on the lattice. And then once you've supplied all this information to model will then spit out the kind of object that you care about. So we'll do this, we'll start by getting quite hands-on with this. And so we'll start by making a simple square lattice. We're just going to go something 2 by 2 for the moment. And then here we construct our lattice object. Here we have the preset for the square lattice. So of course this means that in both directions, and in the x and y directions, we have similar spacing between all the sites. And so we pass the square preset, and then we pass it a list of basically the lengths of the square lattice. And so here we made it, we just passed the list from these two. Then what we do is we construct our model object. So now, once we've built our lattice, we just feed it, we feed model a lattice, creates the model lattice. It creates a model for us. Now, from this, we need to start giving rules to the model, so as it can actually start to figure out when it's going to create these structured operator sums for us, how exactly are things going to be related. So we're going to start with model. We're going to take our model M, and we're going to add rules to it. So the first rule that what we're going to do first is a general rule is made up of effectively kind of a coefficient, eventually an operator living on some bond, but we need to first tell our lattice what kind of rules around our local sites do we actually want things to be connected with. So first, we're going to use the neighborhood rule. Again, this is an object from the lattice class. So again, if you need help, I would encourage you to go to the docs directly. So then from here, we're going to label our rule, because we're going to use different rules at different times with maybe the same coefficients, so labeling is more simple. And we're going to give it a primitive vector effectively, or some direction in our lattice for this rule to begin thinking about. So this actually prescribes the delta between the sites. So here we're going to create our coefficient, and then we're going to give it two rules. So here we're going to give it a rule in the x direction and then in the y direction. So we've named two bonds, both along the primitive vectors of the square lattice, and we give it a coefficient. So now along these bonds, we would like to give some physics to it. So what we're going to do is we're going to say, okay, we're going to add a term to our model. So this would be really in LaTeX, for example, this would be the sum. One of the sums are in our Hamiltonian. This would be one term in our sum. And so we would give this term, we're going to call it J, and we're going to give it a list of factories to operators. So again, this is the Z, the Pauli Z gate, or the Pauli Z matrix. And so we're passing it a list of saying, okay, along the nearest neighbor of X, or along the X direction for our local site, we're actually going to add these two factories. So these are factories that create operators, and we're going to say, okay, along this direction, as long as you have this rule, you will place this operator on this bond. Same thing for the y direction. And of course it's scaled by j. So what this does is this says, okay, now that you've given our rule, lattice is smart enough to figure out all the details you care about. But here, all we've had to really do is, now that we have this rule, we just give it our operator. And we're going to make this more complicated as we go along, of course, but lattice takes care of this for us. Now, if this is for a two-site interaction, so this is between one site and its neighbor in the x or in the y direction, but we can also do single-site terms. They look a little bit different. So same thing, we're going to add a coefficient, and then we're going to add a term directly, and we're going to say it's going to have a coefficient h, and it's going to have, instead of a list, it only has a single operator acting on the site. So in this case, let's say x, and then we're going to tell lattice effectively, tell model, apologies, that we actually want to have the on-site interaction. So rather than giving it a rule that is custom, this is a built-in one that model knows and can go from there. Okay, so same thing, same pattern. Now once we're done, so let's suppose that we're done, what we're going to do is we're just going to ask model to be converted to an operator sum effectively, and it's going to return to us a real operator sum. So if I run this, here we can see that, of course, this is for 2 by 2, so it's not that big of a sum, but we can see that the sum that's been spit out here is actually quite large, and it seems structured. There's some nearest neighbors, there's some non-local terms with 0 and 2, so something is going on, which is good. So this is a linearized kind of version for you so that you can go and do numerics and everything can be nice and simple for us to use. But usually this isn't kind of enough for us to do anything. Really, you build your model, you have your Hamiltonian, you have some observables that you care about, and what you want to do really is you want to measure some properties of it. So going about measuring is fairly straightforward. So now we're going to go back to our model object, and we're going to use the measure method. And this measure method is basically going to add to the model, or using the ordering that model has now been assigning to all the terms, we can now add an observable that will fit into this ordering. So here we're just going to label effectively what observable this is. We're going to call it the Z magnetization, and we're going to add a term that we want to measure. And this time it's going to be basically the whole magnetization across all the sites. So this will be, we're going to add the Z gate with the on-site again constructor, the on-site string rather. And then we're going to pass this, we're going to make we're going to use a slight conversion. We're going to use observable to opsum, and observable to opsum will turn this observable directly into an opsum. It's going to return to you a map with all the observables you care about indexed by the label that you put them in. Okay, so, and then we can run this again, and it returns to us our total Z magnetization observable. Okay, so that's great, but that was fairly simple. So now we can start to do more complicated things now that we have the hang of it. So what we're going to do here is we're going to now go 4 by 4, and we're going to make a Heisenberg interaction on a square lattice. So we're going to start pretty much the same way, make a model, but we're going to inline directly the lattice construction using square. We're going to pass to the list of 2 directions that we care about. Then we're going to add a coefficient. This will be the antiferromagnetic, well, the exchange interaction, the spin exchange interaction we're going to add j, and so we'll put it as 1, leave things antiferromagnetic. We're going to give 2 rules, again, very similar, along the x direction and the y direction. And now along these directions for these bonds, we're actually going to give different kind of constructors. So here, what we've added in the x direction for these 3 here is we've added XX, YY, and ZZ interactions. But you see here we started to add some anisotropic terms or some symmetric exchange. These are like these gamma interactions that make things a little bit interesting. Sorry, they're not anisotropic. I should retract that. But the idea is that we can arbitrarily start making different combinations of operators onto these sites fairly easily in the y direction or in the x direction, how we care. So this would be an example of a Heisenberg square. But we could also, pick something. We could pick something else here, and we can put, say, a ladder. So using the model class, we can have these various 2D geometries. One common example is the Kitaev ladder, which is basically just a ladder with Kitaev interactions. And so we can do something very similar. So here we're going to choose the length of our ladder, and then we're going to give it a number of rungs and a number of legs. And so here we're just going to provide the 2 kind of lattice coordinates, or kind of our bonds that we're going to have, which is either going to be along the rungs of the ladder or along the legs. So we have a longer length and we have shorter lengths, which are the rungs. And so along these 2, again, we're going to inline the construction of the lattice. Here, we're just going to be a little bit verbose and particular, because we're going to want some very special interaction. So in the previous examples, I showed how we can go across all these different sites and we can apply all these different rules for all these different bonds. But maybe you have some kind of checkerboard pattern that you want to apply. So in particular for the Kitaev ladder, what happens is typically along the legs and the rungs, we might want to have a different alternating pattern for different kinds of interactions. And so what we're going to do is we're going to construct lattice. We're going to use a square lattice, which this just means that the legs and the rungs and the spacing between the sites all have the same site. But we're going to make it 2 by length, 2 by the length, and this length being 4 in this case. And we're going to choose to have open boundary conditions. Again, lattice can deal with periodic boundary conditions as well and takes care of it for you. But here we're going to leave everything open. And so now we're going to add some rules. So now we're going to want some specific interactions along the legs and along the rungs. So along the legs, we're going to want an alternating pattern of x and y. So what we're going to pass effectively to model is we're going to add a rule, a neighborhood rule, where it's a little bit more complicated. Here it's very simple, so we're going to label this x leg. We're going to have it occur across the leg direction of the lattice, and we're going to pass it a function, a lambda, where it's going to check a condition for us. So basically here it's going to check if there's it's going to do an alternation between even and odd. It's going to return true and false. And the idea is wherever this function is true, it shall apply this pattern. And so we can have the y pattern, which is the complement of this, which is, or just the negation of it, and it returns the opposite condition that you get for the x and the y leg one. So basically what we have here is we have an alternating pattern, and then we're also just going to add the rung rule along the rung direction, which is along the x direction, so this is a standing ladder. Okay, and then we're going to add the coefficient. We're going to do k, keep things antiferromagnetic, and then along, very simply like we've done before, we're just going to assign the terms with the rules labeled by the strings that we have here. And that pretty much can take care of many different geometries. So here you could replace lattice with different things. And so now we're going to get into a very quick jumping off point with actually doing numerics. So suppose I want to do I want to generalize this Kitaev ladder. So here I just made a function. I wrapped all of this together, and I'm putting this in a simple function for us to call at the beginning. So we're going to work with the Kitaev ladder, with the transverse realizing model, the one that we had before, but in a chain. But we're going to make it no, not this one. Yeah, so we're going to make things fun, but we're also going to add nearest neighbors, a nearest neighbor exchange as well. So it's not just beyond next nearest neighbors, beyond nearest neighbors. So next nearest neighbors, which is I and I plus 2. So very similarly, we're going to construct a bunch of different examples, and we'll make the Heisenberg model again with these these integrability breaking interactions that we have here. Sorry, no, not in this case. This is not the case. I apologize. Okay, so here, this is the Kitaev ladder basically in 1D. And so, of course, I've wrapped everything in a function, so it looks a lot simpler. Oh, oops. But here, we're going to make the ladder. So right now, this will be for 18 sites, 18 total sites. So what we're going to do is we're going to call our function. It's going to make our model, and we're just going to convert it to an operator sum. So the easiest way right now, I'm going to leave it as complex because we have some YY interactions here and the way that I've designed everything. But the idea is basically that I return the model, turn it into an operator sum, and then I can get going. So we covered in another tutorial, another live session, these iterative eigensolvers. So now we're just going to solve for the lowest lying states. So we're going to get the total number of sites. We're going to get the number of eigenvalues that we care about near the bottom of the spectrum. And so then we have to pass some options. So we're going to first say that our model is Hermitian, or our Hamiltonian is Hermitian. It's not real because it contains some Y matrices. The Krylov dimension will be 8. This is the number of Krylov vectors that you carry. Increasing this number will make things better, but for the moment 8 is sufficient, and we'll choose our tolerance, which basically controls the convergence. It's basically the residual vector error that we get. And then we just pass them to our eigensolver. So we pass the Hamiltonian, the dimension of the Hilbert space, the number of eigenvectors that we care about, and our options. And so we'll collect this with our results. Our results map, we can get the, we're going to print the eigenvectors, and then we're just going to see kind of what the lowest lying energies are. And so this shouldn't take too long. But yeah, so this is a fairly, there are many terms in this. So the Kitaev ladder, if I scroll up, again, it has this rule between x and y. We also, yes, we have the Kitaev interactions, and we also applied here, I apologize, I forgot to mention, we apply a magnetic field in a particular direction. So this is, there are many terms, so this takes a little bit of time, but otherwise it's fairly simple. So in this we've written our ladder, of course, with some complexity carried over, hidden in this function, but the gist is to make things simple and scalable. And as we're going to see later, what's going to happen is that we're going to use the same functions effectively that create the same model in order to make different kinds of operators that we care about, in particular matrix product operators. Yeah, so while this is running, I'll also show the idea here that what we care about, here again for the transverse field Ising model with next nearest neighbor interactions in 1D, we're going to have here, we're going to have this, we're going to have this, okay, this finished. We're going to have similar setup. We're going to give some number of sites. We're going to give some coupling information. We're going to make our model. We're going to turn to an operator sum. Here I can specify that everything is real, which will give us a speed up because everything, it's basically half the memory. So there's less things to track. And so similar setup, this is nearly identical. I copy and pasted this. I just replaced what model was being created and some other options. And this can create the results. So here again, we did it with the 18 sites. It prints the lowest lying energy eigenvalues. And you can keep going from here. And it used only 0.2 gigs of memory, which is good. Okay, so let me just comment this out, and we're going to look at the transverse field Ising model. So here for 18 sites, let's start, we'll start here. Here we're away from the transition, and so if we want to see this, again, we'll just run. But again, I would like to emphasize that the only point here that I've changed is that I've just changed the model that's being created, which again is hidden in those functions, but is going to be rinse and repeat for many things. So here, this is a 2D example, again, while the other code is running, that this is essentially the same thing, except so all the complexity is being absorbed by model, and we can just view different kinds of physics for different phases. So one, we saw a ladder. Now this is a chain that's running, and this will be in 2D. And so it's very straightforward with this regard. Okay. So now for the last step, so now we saw different geometries. The last thing will be to look at, and then it's finished, which is wonderful. So again, here I'm going to take the transverse field Ising model chain. So we're going to stick with this one for a little moment, and we're going to start playing around with extending this. So we were stuck at 18 sites, or we can go beyond 18 sites. And we can push this to bigger and bigger numbers. If you have more patience, this took 46 seconds. For the purpose of the video, I will not increase this further. But if you did, say, want, for some reason, 18 to go incredibly fast, you could use tensor networks. So tensor networks are an approach in which there's a compression of the many-body wave vector. So if you go to our documentation again, we have a section on this as well. So many-body, where is it? No, many-body. Sorry, it's in tensors, and it's in linear tensor networks. So effectively, when you're solving these problems numerically, there's an exponential number of degrees of states you need to track. And so one compression you can do is you can compress your many-body wave function to a tensor network, which is a approximation of the full many-body wave vector with a polynomially complex object called a matrix product state, which is suitable for one-dimensional geometry. So we're not going to go to 2 dimensions for the moment, but effectively you can read more about this here. But the idea is that you can have a lot of simplified, using some simple assumptions, you can reduce the complexity and have a representation that is much more scalable and also incredibly efficient at approximating ground states of one-dimensional models, in particular when there's a gap. So what we're going to do is we're going to use the same model system to use this tensor network approach. And what we're going to do is, in order to use MPSs, you need to use what's called a matrix product state. So basically, this is a very similar decomposition of the whole matrix of the whole Hamiltonian into a local decomposition of the Hamiltonian in terms of tensors. And these matrix product operators act on matrix product states. And this is the bread and butter of DMRG, effectively. And so DMRG is an update scheme in which it's a variational approach to get the ground state wave function of a one-dimensional system. And so we can combine all of this, and there's some complexity in just getting these objects to work and interact in and of themselves, but then for different geometries, it gets rather tedious. So with the model class, basically, this is the same function I've had before, and we're going to use this as our starting point. So what happens here is, so we're going to need a couple of things. So we're going to pass the number, the lattice size, which will be 18. It's in one dimension, so there's 18 sites. We need to pass a physical dimension to our tensors. So here, there is a variational parameter called the bond dimension. And this basically says when we decompose our full wave function into this linear train of tensors, we need to choose this. We can tune the choice or how big the size of the tensors are. And the bigger the tensors are, the more they capture in principle. But it doesn't necessarily mean that bigger is always better. It could be that actually there is an optimal bond dimension that just works best for the update procedure. But in general, the bigger it is, it actually will recover the accuracy of the full wave function. So it increases in general the physics that's captured. But the physical dimension is not the bond dimension. I apologize. The physical dimension labels the index, so the spin index. So it will be up or down for each site in this case. And so the physical dimension is 2 for every tensor. So you think of it as 2 copies of tensors on every site. And we pass the parameters. Same thing. This is tensor agnostic. We make the transverse field Ising model chain. Then we convert this to an MPO. The MPO is this Hamiltonian expressed in this tensor framework. And all you need to do is really just pass the model to the MPO constructor. And that's it. So there's nice integration between some higher level operator stuff and our tensor network library here. Okay. Next, what we need to do is we need to give an initial state to seed our ground state search. So here we're going to make a random MPS. This is standard practice in performing DMRG. So what we're going to do is we're going to give it the number of sites. We're going to give it the physical dimension, which is 2. And then we're going to give it the bond dimension of 4. So the bond dimension will change, and how you change it is a whole thing that we're going to get into next. But the idea is first you want to ensure that you have a good start. A random choice is good, and we're going to make it complex for the sake of it. We're going to normalize it as well. And then we are going to choose our options. So for our options, we need to choose, like I just mentioned, how we're going to update our bond dimension. And this is what's called the schedule, or the bond dimension schedule. And so we have different ones. By default, we choose a logarithmic one. So basically an update rule for how at each step when we perform sweeps, or we go through our matrix product state and we update it slowly, how do we actually give it the nudge so that it gets a better approximation? And so here we're going to pick a logarithmic update. This is rather controlled, and it's rather stable. There are others that exist. You can use a polynomial one rather than a logarithmic one. This has a couple of different sub things that it includes, namely linear growth. So if you want the bond dimension to grow linearly, or with the square root, basically you have some control over how you would like things to change, and there's no general schedule that works best for everything. It's always going to depend on your system, your physics, and what you expect. So that's the schedule. The max bond dimension, sometimes you have memory constraints, sometimes for physics reasons you might want to constrain the bond dimension to ensure that it actually searches the solution space correctly. So you can cap it here. In this case, for the transverse field licensing model, we know that the bond dimension shouldn't be too large. So we can expect this to be 80 is fine. For bigger systems or for molecules, like some linear molecules, you might need to go to the thousands to get a good estimate of the ground state, but here 80 should suffice. Maximum number of iterations that we want our whole DMRG to proceed. We don't want it to run too long for no reason. We also don't expect it to run too long either, because the solution should be found rather fast. The energy accuracy, this will determine the precision we would like the energy to. The truncation accuracy is the truncation of so it's related to the bond dimension. Effectively, what happens during this update is that there is the use of the singular value decomposition. And since we're doing this numerically, we can actually choose the precision of the decomposition as well. So we typically want the truncation accuracy to be rather good, because if we start throwing away some singular values too early, we actually lose information and accuracy that we would otherwise need. And lastly, we're just going to give some printing information for during the runtime of the algorithm to see kind of what's going on and ensure that everything is going well. So now that we have those covered, what we want to do is we want to just run DMRG. We're going to pass it our initial state. We're going to pass it our MPO, our Hamiltonian in MPO form, and our options. And then we're going to recover the ground state energy and print some little things here. So we're going to put this here, and we're just going to run it. And it's basically it's almost instant. So DMRG is incredibly powerful. So it took is that 10? A factor of 100? Is that 100? I think it's 100. It's basically, it's 100 times faster than what it took for our exact calculation, because it's an incredibly efficient algorithm. But we can push this again. We can keep going. And here, okay, so now we doubled it, increased by 10, but the idea is that we can see here, we printed some information, we start off with some energy accuracy, and we can see that as we start to get to the later sweeps, we have our convergence at around 41 sweeps. So everything is going well. And yeah, so I encourage you guys all to play with our DMRG and to start building some interesting spin models. But all in all, the idea was that we use the same kind of functions and construction using model to generate some starting off points for our numerics. If you guys have any questions, please join our Discord and ask some questions and some features if you would like. But if anything here wasn't clear, or you would like access to the code, just make a request in the showcase. And I'll gladly post the code there for anyone who would like to use it. And as usual, thank you for your attention, and I hope you guys have a great day.